Hi everyone. So in this video, we're going to be talking about another method for computing the volumes of solids of revolution. So this method is going to be really similar to what we discussed in the last video. The main difference is that in the last video, we were finding the volumes of shapes where when you sliced them, the slices that you got were these circular discs, right? And so that's why we called it the disc method. And so in this video, we'll be looking at shapes where when you take a slice of them, instead of having just one circle, you have a circle with a smaller circle within it. So kind of like a hole in the middle. So we'll see what that looks like when we get into our first example. So in this video, we're going to do 4 different examples. So kind of like in the last video, the first 2 will be a little bit more straightforward, and then we'll do 2 other examples that are a little trickier. So the first example we want to do is we're going to find the volume of the solid generated by revolving the region bounded by. So the curves we're looking at in this graph are going to be y is equal to x and y is equal to x squared. And we're going to revolve that region about the x-axis. Okay, so let's sketch this graph, and notice I really zoomed in. It's because the region we're going to get is really small, and I think we have the best chance of actually seeing what it looks like if we're really zoomed in. So y is equal to x squared is going to be a parabola, right? So it's going to come in like this, and then I'm going to focus on this part because this is the part we're really going to be looking at. So it's curved like that, right? I probably exaggerated it a little bit, and actually I need to redo that because I only want the right side. So let me just redo it like that. Okay, so something like that. And then the line y is equal to x, well, that is just going to be a line that goes, oh my goodness, straight across, right? Slope of 1. So the region we're talking about is this region here, this kind of little sliver that is between y is equal to x squared and y is equal to x. So, and let me maybe just extend these a little just so that when we're referring to them, it's clear what is what. So the parabola is the bottom part, right? And the line is the top part. So what kind of a shape are we going to get if we revolve this around the x-axis? So we're revolving it like this. So I'm going to start by, again, like I did in the last video, drawing kind of the side view. So it's going to look something like this. And it's a little confusing, I think, especially in this picture to add this in, but I just like to add in this kind of 3-dimensionality just so that you can remember that this is a 3-dimensional shape. So when we're looking at this picture, you're kind of looking at 2 things simultaneously. So if you were to kind of cover up the part that we shaded in, you would see that from the outside, it looks kind of like a cone, right? Like a very kind of flat cone. And that's why I added this circle at the end to really emphasize that, that cone shape. But if you were to look kind of inside of the cone, you would see that it's not filled in. It has actually a hole in the middle, right? So like this whole part is empty, right? Because the part that we're revolving around is just that outside purple part. And so from the outside, it looks like a cone, but on the inside, it's hollow. So I'm just going to show you a couple of different images that might help you kind of understand that. So these are just things I found online. But these are just kind of like 3 different views. So if you look from the outside, that would be like this one, right? From the outside, it just looks like a cone. If you then take a peek into the inside, like in this one, you'll see that it's hollow in the middle. And then if you think about what it would look like if you cut it, well, it has kind of this thickness to it, and each slice would look kind of like a donut, right? So they're only showing one little section of it. And we'll see in a moment why we're going to call these things washers. But basically you have, if you were to cut it, you would have this like ring, right? You would have one bigger circle representing the outside and one smaller circle representing the inside. So let me just show you one more visual for this before we get into actually calculating. So this is the same or a similar thing as I showed you in the last video, I found that it doesn't work quite as well for this method for these shapes that have a hole in the middle. We'll see. I don't know. I just feel like the visual isn't as good, but it's still somewhat helpful. So here you put in both equations. So we put in f of x is equal to x and g of x is equal to x squared. And so notice that the area between them is getting filled in with these rectangles. And, you know, the rectangles aren't doing the best job of approximating that area between them, but, you know, it's okay. And so I'm going to rotate these around. And so now if we peek at it from this side, we can see that we have, you know, something that's kind of hollow in the middle. And each of these slices, rather than being a disc, they are these slices that have a circle on the outside and then another circle on the inside. So why is it that we call these kind of discs with a hole in the middle a washer? Well, that's just a name of a type of piece of hardware. So I just want to quickly show you so that you know when we call this the washer method and we keep saying the word washer, I just want you to have something in mind. So a washer is something like this, right? It's a piece of hardware that is like a disc, but with a hole in the middle. When I say washer, I don't want you to be picturing a dishwasher or a washing machine. So that is not what I mean when I say washer. When I say washer, I mean a shape that looks like this. Okay, so let's go back to our example and see how we can calculate the volume of this shape. So the volume, we're going to start with basically the same formula. So I'm going to go back to the original formula that I wrote down. That was the integral from a to b of the area of the cross section dx. So in the last example, in the last video, we, instead of using this area function, we just said pi r squared, right? Because that was how you found the area of a disk. In this case, because the cross sections are not disks, they're washers, we're going to have to do something a little bit different to find the area. So let me just move this a little bit out of the way. So in this case, the slices, so if you were to imagine, again, going back to the last video, adding up all the volumes of all these slices, look like washers, not disks. And so how would you find the area of something that looks like a washer? Well, if you think about it, if you have a circle with another circle cut out, and let's say you're trying to find this area. Well, all you would have to do is take the bigger circle area and subtract out the smaller circle, right? So the way we're going to do that is we're going to call this smaller radius, the radius of the smaller circle, we'll call that lowercase r. And then we'll call the radius of the bigger circle uppercase r. And so the area is going to be equal to pi times big R squared minus, let me actually color code this a little bit different, pi times big R squared minus pi times little r squared, right? That is how you would find the area of that shaded part. And another kind of nicer way to write this is we can factor out the pi, and then we're left with big R squared minus little r squared. So now our job is to basically figure out, just like we had to keep doing in the last video, we had to figure out, what is the radius. In these examples, there's going to be two different radii that we need to figure out. So let's go back to our picture and try to figure out what is the bigger and the smaller radius. So I'm going to draw a sample washer here. So just going to draw like a circular piece and then like another circle on the inside, and then just draw a little thickness to it because that's where the dx comes from, right? Okay, so what would be the smaller radius in this case? So little r would be equal to x squared, right? Because that's the one, if you look at what is the curve that's at the bottom, that comes from the parabola. And then what would the big radius be? So that would be measuring all the way from here up to the outside, the very outside of the shape. That would be determined by y is equal to x. So the big radius is equal to x. And so when we go back to our integral, we're going to be integrating. Now we can pull the pi to the outside. Actually, let me write it in multiple steps. So we're going to be integrating again the area of a cross section. And to get more specific in this case, the area of the cross section is pi times big R squared minus little r squared. And then just to make our lives a little easier with the integration, we can pull out that pi. And so this is going to be the general formula we'll be using for the washer method. And I'll write that out more officially after we're done with this example. So in this case, we saw that our big radius was equal to y is equal to x, right? So that part is just equal to x, and then the little radius was equal to x squared. So we're going to go and put those into our integral. So we have the integral, and we'll talk about the bounds in a second, so the first radius, or the big radius, was x, and the little radius was x squared dx, and then we need this pi that I dropped. And then what are the bounds? Well, the bounds work exactly the same way they did in the last video. So the bounds are just going to come from what is the smallest x value where you're drawing a disk, and what's the biggest x value. And so we start at 0 and we end at 1. And so our bounds are from 0 to 1. And so this is going to come out to be pi times the integral from 0 to 1 of x squared minus x to the fourth dx. And so if we take our antiderivative, that's going to be x cubed over 3 minus x to the fifth over 5. And we're evaluating those at 1 and at 0. And so we end up with pi times 1/3 minus 1/5. And so if we put these together, so if we make a common denominator of 15, that's going to be 5 over 15 minus 3 over 15. And so we're left with 2 pi over 15 as our final answer. So again, same setup as we did before. The only difference is that because the cross sections are no longer circles, they're these washer shapes. Instead of putting in just r squared, we have to do this big R squared minus little r squared. So let's just write that down as a general fact. So if a solid of revolution is revolved about the x-axis, or as we'll see, a horizontal line, and its cross sections are washers. So I didn't really say this in the last video because I didn't want to kind of add complication, but really when I wrote out this kind of similar statement in the last video, I should have added that the cross sections have to be disks in order to make that true. So, and it's cross sections, sorry, I wrote the wrong word here, are washers. So in this case, then the volume is going to be pi times the integral from a to b of big R squared minus little r squared dx, where big R is the outer radius of the washer, and little r is the inner radius. So I drew a picture that I think helps illustrate this on that other page. I'm not going to redraw it, but you can refer back to the other page if you want to see what we mean by the inner and outer radius. And then a little later, we'll come back and basically write down the same thing with respect to y. So very similar to in the last video. If instead you're revolving around the y-axis, then we just basically have to change this definition to be in terms of y. One thing I just want to quickly mention that is kind of a common misconception is that be really sure that when you're doing these, notice that big R squared minus little r squared, that is not the same thing as big R minus little r squared. So it would not be correct to be doing the integral from a to b of big R minus little r squared dx. That is not correct. So why is that not correct? Because if you think about where did we get this from? Like why is this here? Well, this is here because of the way that you find the area, right? Going back to this other picture, we found the area by taking the big circle and subtracting out the little circle. And so each of these r's are getting squared individually. So it makes no sense to subtract those values and then square them. So make sure that you're not doing that. Okay, so a few more examples. So next example we're going to do is we're going to find the volume of the solid obtained by revolving the region bounded by. So in this case, our curves are going to be y is equal to e to the x, y is equal to 3, and and x is equal to 0. And we're still going to be revolving about the x-axis. So we want to start by drawing our region. So we have y is equal to e to the x. So I'm just going to kind of roughly sketch that. So that means that when x is 1, y should be approximately 2.72. And then it has a horizontal asymptote off to the left, and it has a y-intercept of 1. So let me try to do a better job of drawing this. It's a little weird because I changed the scale on this so that it would be easier to see what's going on. So the shape looks a little different than what you might usually think of it looking like. Okay, what else do we have going on here? We have x is equal to 0, and we have y is equal to 3. So that means that this is the region that we're revolving around. And so we're revolving it around the x-axis. So what kind of a shape is this going to give us? Well, let's start by reflecting it and seeing the shape from the outside. So we're going to have a similar kind of curve like this here. Oops, I shouldn't shade that in. Okay, so that's what it would kind of look like from the side if you were to cut it. And then I'm just going to add this in. The bottom is curved, right? So I'm just going to add that there. And then the top is also curved. So we have like how I would describe this is from the outside, it looks like a cup or like just a cylinder, right? Like the outside has completely flat edges around the outside. But if you were to peer in the inside, you would see, oh, actually the inside is kind of curved, right? So like from the outside, it just looks like a ring with flat sides, but the inside, if you look at this purple part, it kind of slopes inward. Okay, so what would be the way to find the volume here? Well, again, we wanted to use this formula where we're going to do pi times the integral from a to b of the big radius squared minus the little radius squared dx. And so still dx because we're still revolving around the x-axis. Okay, so let's draw a sample washer here. And I know this is kind of a little bit of a clustered picture. So maybe in this case, I'm actually just going to get rid of those because I think they might just make this a little too cluttered. But just remember that we are looking at a three-dimensional shape here. So this is what one washer would look like, right? So it would have this kind of outer part and this inner part, and then I'll give it a little bit of thickness. Okay, so what does the outer or the inner radius look like? It's like this, right? So that's our inner radius, and then our outer radius is going to be going all the way to the outside there. So what is the inner radius? Well, the inner radius is determined by the graph of y is equal to e to the x, right? Like that's if you were to try to find what's that green distance, you would have to plug in whatever x value you have into y is equal to e to the x. And so the little r is going to be equal to e to the x. And then what about the big R? Well, this one's a little bit different because notice that no matter where you go, no matter where we drew this washer, the big radius would always be 3, right? The little radius is going to change. It's going to get smaller over here and bigger over here. But notice that if you were to, draw the big radius at any point, it's always 3. And so in this case, the big radius is actually constant. And that happens sometimes. It really depends on the situation. And that's why it's so important to draw a picture and understand what's going on in that specific situation. Okay, so let's put these values in. So we're going to have pi times the integral. And so our bounds, again, we're just looking at what is the smallest and biggest x value that we're looking at here. So actually, in this case, there's a little bit more that we need to think about. And so let's come back to that in a moment. I want to just put in our radii first, and then we'll come back to that idea. So the big radius is 3 squared. The small radius is we have e to the x, and we're squaring that. Okay, so the smallest x value, that one is fairly simple, right? It's 0. How would we find the biggest x value? So this one's a little bit tricky. I know it looks on the bottom like it's 1, but that's actually not correct, because if you look at the top part of the graph, I just didn't draw it perfectly on the bottom. So what is this final x value? Well, it comes from the place where e to the x and 3 intersect. So if we wanted to figure out what that point is, we would need to set e to the x equal to 3, right? And if we solve that for x, that will tell us what that x value is. So that x value is going to be ln of 3, right? So if you wanted to solve this for x, you would find that, I don't know why I wrote that, x is equal to ln of 3. And ln of 3 is just a number. Remember, like I think there's a temptation when you see ln or e, you think it's a function, but ln of 3 is just a number. So it's totally fine to have that as a bound. Okay, so let's go and actually evaluate this integral. So we're going to have pi times the integral from 0 to ln of 3 of 9 minus e to the 2x. dx. So when we go and find the antiderivative, this is an example of one where you could use u substitution. I'm going to do this without substitution just because I think situations like this are ones where I think it's to your benefit to be able to do it without substitution. So I'm going to kind of walk you through my reasoning for coming up with the antiderivative, but just know that if you wanted to use substitution, so in this case you would be setting u equal to 2x, that's totally fine. That would work. It would be great. I'm just going to do it another way because I think it's a little more efficient. So what would we want to do in this case? Or sorry, let me start taking the antiderivative. Well, the first part of the antiderivative is just 9x, right? So what would be the antiderivative of e to the 2x or negative e to the 2x? Well, if you were to guess negative e to the 2x, the problem would be that when you take the derivative of that, you would introduce an extra factor of 2, right? So you can always guess and check antiderivatives by taking their derivative. So if we're looking for the antiderivative of e to the 2x, it's not going to be e to the 2x, it's going to be e to the 2x over 2, because you need that extra factor or extra divided by 2 in order to cancel out the factor of 2 that would appear when you take the derivative. And now we're going to evaluate this at ln of 3 and at 0. Okay, so now we have pi times, so we can plug in ln of 3 first of all. So we have 9 times ln of 3. I'll actually do that without parentheses. So that's just a number. 9 times ln of 3 is some number. And then we have minus e to the 2 ln of 3 divided by 2. And then from that, in this case, we actually do need to plug in 0 because whenever you have e to a power, if you have e to the 0, that's 1, right? So that's not going to cancel out. So we're going to get 0 minus e to the 0 over 2. So that's going to be negative 1/2. Okay, so what goes on here? So now we have pi times 9 times ln of 3. So let's talk about how to simplify e to the 2 ln of 3. I'm going to kind of take this off to the side to talk about how to simplify it so that we're not getting all messy in our work. So what we currently have, I'm just going to work with e to the 2 ln of 3. So another way of writing this would be e to the ln of 3 squared, right? That like would multiply that together and it would be e to the ln of 3 squared. And then what is e to the ln of 3? Well, that reduces to just 3. So why is that? It's because ln is by definition the number you need to raise e to get 3. So ln of 3 is equal to some number. You could figure out what it is by typing it into a calculator, but it's specifically the number that you need to raise e to get 3. That's the definition of ln. And so if you take e and raise it to that number, well, of course you're going to get 3. That's just the definition of what ln of 3 means. And so we have 9. So that actually simplifies quite a bit. So we're left with 9 times ln of 3 minus 9 over 2. And then this becomes plus e to the 0 over 2 is 1/2. So we're almost done. Our final answer is going to be pi times 9 ln of 3 or minus, so 9 halves plus 1/2, or negative 9 halves plus 1/2 is going to be negative 8 halves, which is 4. And so this is our final answer. Okay. So next up, this one is going to be now a revolution around the y-axis. So we're going to find the volume generated by revolving the region bounded by, so this time we're going to do y is equal to square root of x, and y is equal to x squared. And we're going to be revolving this about the y-axis. Okay, so the region is actually going to look kind of similar to the very first example we did, because half of it is going to be, so we have y is equal to x squared, that's this kind of parabola shape. And then y is equal to square root of x is actually just kind of the opposite shape, right? Because they're inverses of each other. So they're really kind of the same shape, just reflected over the line y is equal to x. And then I'll just extend them a little so we can kind of keep track of what's what here. So this is y is equal to x squared, and this is y is equal to square root of x. And so we have this region here. And we're taking this region, and this time we're revolving it around the y-axis. So we're going to get a shape that kind of looks like this. And if you were to look from the outside, it would look circular. It would look kind of like a bowl, right? Like a round bowl. But then the inside of that bowl would be kind of funny. It would be like, it wouldn't be rounded. It would kind of like almost get pointy at the bottom. So it would be a strange bowl. Okay, so in this case, if you draw a sample washer, notice that the thickness is going to be dy instead of dx. And so that's what tells us we need to integrate with respect to y. And so really all that means is that, just like we did in the previous video, we need to switch our equations to being functions of y instead of functions of x. So that's actually not too hard, because they actually, we're going to see they're just going to kind of switch. So y is equal to square root of x can be written as x is equal to y squared. And then y is equal to x squared can be written as x is equal to square root of y. So we end up with like the same two functions, just the one that's on the top and the bottom are kind of flipping from each other. And actually, let me do this in another color, because I forgot I was using orange for something else, and I want to be consistent here. So this is going to be x is equal to square root of y, and this is y is equal to x squared. Or sorry, x is equal to y squared. Okay, so let's find our radii. So the inner radius is going to be determined by this, this top curve, right? And so this top curve is y is equal to square root of x, or x is equal to square root of y. And so we want it as, or sorry, y squared. So we want it as a function of y, so we're using y squared. And then the outer radius is going to be using the bottom function. And so that function was originally y is equal to x squared, but we want to write it as square root of y. X is equal to square root of y. Okay, and so the volume is going to be equal to pi times the integral from a to b of big R squared minus little r squared dy this time. And so in this case, that's going to look like pi times the integral. So this time we want to put in y value. So the smallest y value is 0. The biggest y value is 1. And then we have, for the first one, we have square root of y squared. And then we have, for the second one, y squared squared. So that's going to be equal to pi times the integral from 0 to 1 of just y minus y to the fourth dy. So our antiderivative is going to be y squared over 2 minus y to the fifth over 5. And we're evaluating at 1 and at 0. So that's going to give us pi times 1/2 minus 1/5, and then if you plug in 0, you just get 0, so we can skip that. And what is 1/2 minus 1/5? Well, if we make a common denominator of 10, we'll have 5/10 minus 2/10, and so we're going to be left with pi, or let's say it as 3 pi over 10, and that's our final answer. So I'm just going to go back and add so a similar statement to what we said here, but just in terms of y. And I'm not going to write out this whole kind of thing just for the sake of time during this video. But basically what I want to say is that if revolving about the y-axis or a vertical line, then we're going to have v is equal to pi times the integral from a to b of big R squared minus little r squared dy. So just kind of what you would expect. All right, so last example we're going to do is going to be now revolving around a line that is not an axis. So it's a little bit trickier, kind of like what we did in the last video. So this time we're going to be working with actually the same region from the beginning problem. So we're going to be working with y is equal to x and y is equal to square root of x. But this time we're going to be revolving around a horizontal line instead of the x-axis. So find the volume of maybe in the future I'll write these problems out before starting the video. In class, I like to write them on the boards because that gives everyone a chance to catch up and write stuff down. But you can pause the video, so maybe I should just have them written ahead of time. By revolving the region bounded by y is equal to x and y is equal to x squared, and we're going to revolve it about the line y is equal to 2. Okay, so let's sketch our region in here again. So again, that was this, we have y is equal to x looking like this. So this is y is equal to x. And then we had y is equal to x squared looking like this. And so this is the region that we're looking at, this little sliver. And this time we're taking this region and we're going to revolve it around the line y is equal to 2. So I think this is a little bit harder to kind of visualize what's going on. So what I want you to picture is, picture that somehow like the shape that we drew is attached to this, to the line y is equal to 2. Maybe there's like a wire attaching it to it or something. And so when we spin this, this thing around, the purple shape is going to stay at this kind of distance away from that line. So it's always going to be, it's never going to be any closer than 1 to the line, right? If we look at what's going on here, like the very closest distance that this shape is ever from the line is 1, and the very furthest is 2. And so that same relationship is going to be true when we flip it all the way around. So what's going to end up happening is that we're going to maintain that distance there, maintain that distance here, and so it's going to look like this. We're going to have the shape over here. And so it's still this kind of like donut shape. It's just that it has like an even bigger hole in the middle than the other one. So I'll add this in. I think in this case that will kind of help visualize what's going on. So it's like this kind of mounded shape. And in this case, actually the inside is, and maybe I'll just do it like that. Yeah, let's do it like that. So in this case, the inside has these kind of flat insides, but the outside is rounded. Okay, so let's look at a sample washer here. And this is where we're really going to have to be careful about figuring out what the radii are. And I'm going to actually get rid of this for now so that we aren't looking at so much clutter in our picture. And I apologize, I feel like this picture is just, it's a little bit too small. I did my best to make it good, but because this sliver is so small, it's just hard. Okay, so let's first start with the small radius. So we need to be able to draw in the picture what is the small radius. So the small radius is this, right? This distance here is the small radius. So what is that distance going to be? Well, if we look at, what is it that is really influencing that distance, it's the line y is equal to x, right? Like that's kind of our best guess. However, the line y is equal to x is not going to give you itself the radius, right? Because if you look at, so let's say that you're at x is equal to 1/2. If you plug that into the equation y is equal to x, that will give you this distance. So this distance here is x. This distance that we're looking for here is little r. And then what is this whole big distance here? Well, that is equal to 2, just looking at the picture. And so similarly to what we did in the other example, we need to do some kind of adding and subtracting. So we can see from this picture that if you take r plus x, that's going to be equal to 2. And so that means that r is equal to 2 minus x. Right? So we got the x because that came from the flat part here, but then that wasn't the radius, right? That gives us the blue height. The actual radius we're looking for is this green thing, and so we had to kind of play around and use this height of 2 and subtract out x in order to get what we were looking for. So I'm actually gonna, I think, copy this picture so that we can repeat this process for big R without me having to erase this. So let me see if I can do that successfully. Sorry, I didn't really think about that ahead of time. Hopefully this will work. Okay, so I don't want all of this. Let me get rid of this. Okay, so now we can focus on finding the big radius. So the big radius in this picture would be coming from the center here all the way to this outer part here, right? So this is going to be our big R. So that, again, we can't just use on its own one of the functions, but what you might notice is that this distance here, that is determined by y is equal to x squared, right? So this distance in blue, that is x squared. And then this distance here is 2 again, right? So that tells us that if we wanted to find big R, we would need to use the fact that x squared plus big R, so big R plus x squared, that's going to be equal to 2. And so therefore, we can conclude that big R is equal to 2 minus x squared. Okay, so now we're ready, right? Now we know what big R is, we know what little r is, and we can go and put those into our integral. So we're going to have the volume is equal to pi times the integral from a to b of big R squared minus little r squared dx in this case. Okay, so let's just put in the values that we found. So we found that, so the bounds should be, again, from 0 to 1, because we're looking at what are the smallest and biggest x values that are a part of this, and that's 0 and 1. So for big R, we had 2 minus x squared. So we're taking our big R and we're replacing that whole thing with 2 minus x squared. And then for little r, that one we found was just 2 minus x. So we're going to put that in for our little r. So this one, there's going to be a little bit more computation. So as always, if you want to pause the video and work it out yourself and come back rather than watching me go through all of this, feel free. So if we were to multiply this out, we would get 4 minus 4x squared plus x to the 4th. Minus 4 minus 4x plus x squared. So we can do some simplification. So we end up with 4 minus x squared, minus 4x squared plus x to the 4th, minus 4 plus 4x minus x squared dx. So what can we combine here? Well, we have a 4 minus a 4, so that's going to go away. But we're still going to be left with now, let's see, we have x to the 4th. And then we have negative 4x squared minus another x squared, so that's minus 5x squared. And then we have just 1 plus 4x. So that is going to give us as our antiderivative x to the 5th over 5 minus 5 over 3 x to the 3rd plus 4 over 2 x squared, and we're evaluating at 1 and at 0. So that's going to give us now 1/5 minus 5/3 plus 2. Now we're almost done. We can just make a common denominator. So that's going to be 3 over 15 minus, so if we multiply this one by 5, that's 25 over 15 plus 30 over 15. So altogether, that's going to give us 33 minus 27 is 8, or sorry, minus 25 is 8. And so we're left with 8 pi over 15. So this problem was very difficult. If you look at this and you're overwhelmed, I understand that it is hard, but take it slow, go to a particular x value and really kind of think about how would I find the different radii I need. And recognize the fact that it is possibly going to be challenging for you, but if you just try to kind of grab a formula that you found online, it's not going to work in every situation. So you really want to be able to draw the picture and analyze what's going on in the specific situation that you're working with. All right, that is it. So the next video will be continuing to talk about volumes. And like I said, we're going to spend probably about 3 more videos on the topic of volumes. All right, I'll see you next time.